So, in the last video we have seen how to solve Laplace equation in a rectangular domain with boundary conditions being Dirichlet conditions. That means you provide as a model, if you look at the plate problem. So, heated plate initially at some temperature, and if you have a boundary and the boundary of the plate is kept at certain temperature. So, what is the steady state temperature in the plate can be calculated by as a solution of this boundary value problem. So, that is what we have seen. Today we try to see the same thing, steady state solution. We will try to look at the solutions for the Laplace equation with boundary conditions being Neumann type. That means you give flux conditions, okay. A normal derivative is provided instead of function itself, instead of the data is being the function, its normal derivative is provided. So, physically for the plate, if initially at some temperature, so once for the heated plate, once it reaches the steady state, and if the boundary conditions, if the boundary of the plates are insulated, then you say that it is a well posed problem, okay. So, you can find the steady state distribution of the temperature inside the plate, you can find out. So, just by solving this problem, okay. So, to do this it should be well defined problem. That means suppose you consider a plate, you consider again a plate. So, what we are providing is here, this is the normal derivative. So, this is this is the data is, this is 0 0 0 a and 0 to 0 b and a to b. So, this is the plate you have, and here the normal derivative is dou u by dou y, okay, dou u by dou y at x. So, this is a 0 at x and y 0, okay. So, this is here normal derivative is, so this is what is provided as f1 of x. So, here the normal derivative is dou u by dou x at x is a, y equal to g2 of y. Here dou u by dou y at x b is f2 of x, and here dou u by dou x at 0 y is g1 of y. So, this is how you provide data instead of as a solution. Suppose f1 f2 and g1 g2 are 0, that means for the plate is being insulated both ends, all along the boundary plate is insulated. That means the flux is neither is going neither, so it's basically is insulated, no heat is going out of this surface, okay, out of this boundary. So, if you really want a steady state of a heated rod, okay. So, what you need is you should not have a source, so no heat should go out. So, effective heat should not be, so net heat either going outside or coming inside should be 0, okay. So, no exchange between no exchange out through this boundary, heat should not go out or enter this plate. In that case you can find you can reach the steady state. Otherwise, suppose you say some heat is constantly coming inside. So, net flux is non-zero. So, that means flux, let us say, which is coming inside, you will never reach the steady state. So, if you want a steady state, whatever comes in should go out, okay, then it can be at some steady state. For example, G1 is the entering through this surface, you want G to be minus G1y. So, the integral value, so integral, so like here and here should be compensated the same way. So, physically that is what is the meaning. So, in a plate these two can be insulated, these two boundaries, but these two can be non-zero, saying but you cannot give any data here. So, any flux data, only thing whatever comes in should go out, then only the steady state will be maintained. So, if you want this G1 to be here, you need G2 to be minus G1 of y, okay. That way you can obtain the steady state and get the solutions for this problem. So, let us so why we make insulated these ends f1 and f2 are 0, because if you want to solve, so you can have this you can also have f1 and f2 as non-zero solution, non-zero flux here, but again here also f1 has, so f2 has to be minus f1 or f1 has to be minus f2, okay. flux should be whatever comes in should go out. So, something like that, okay. Heat whatever is entering, if it is positive it is entering whatever. So, okay. So, it is whatever goes through these two, so net flow out of through these two boundary should be 0. Similarly, these two should be 0 physically, that is what is the meaning. Actually throughout, if you would say throughout, if as 4 boundaries, if you say all these 4 boundaries, integral, if you call this as a boundary, integral over b whatever your u, not u, so dou u by dou n is the normal derivative should be 0. So, this one can show. If you want to have a solution, it is necessary that this has to be 0, okay. So, we will first show that this necessary condition is always true, okay. Physically, that is what you can easily see. If you want a plate to have a steady state, no heat should enter or heat should not go out of this, okay. Effective heat should not go out. That means whatever, if at all there is a source of heat coming from outside, what it should be, it should go out by some other means, some other boundary, but if it comes through this boundary, should go out that boundary, okay. So, we will see how we will prove this one. So, for this let us consider, let u of x y and v of x y be two solutions of Laplace equation. Laplace equation is uxx plus uyy is 0, okay. Then you can write the Green's formula from the calculus. So, this is your d, if this is your d and boundary is b. So, I have not taken actually the plate, general domain d, this you call it d, the boundary is b. So, if you take this over this, you take this v and then you have a Laplace equation, you can also write gradient square of u equal to 0, okay. So, gradient square u minus u gradient square v, this is what is a Green's function. So, this is dx dy, this is the double integral because this is a plane area, this is equal to, now you have a line integral that should be a closed curve over b v dou u by dou n minus u dou v by dou n, oriented curve, okay. Some kind of orientation you have chosen. You have a curve orientation always such that your domain is, the d is always on the left hand side, then this is true, otherwise you may have to take with minus sign. So, let be the solutions, you can see that v, if I take it as 1, constant 1, if v is 1, it satisfies the Laplace equation, the derivatives are 0. So, v is 0, let v u be the solution as usual, okay. So, if you put v equal to 1, what you get is, so del square u, since u satisfies this equation, this is 0 and v is 1, so del square v is 1 is 0. So, the left hand side is 0, the right hand side is, so over b, v is 1 dou u by dou n 1 here minus u into dou u by dou n, the derivative of constant terms is 0 of, this is dv, let us say, okay. This is like a line integral, okay. So, this over db is 0. So, this is nothing but integral over b dou u by dou n into db, this is b, okay. B is the parameter of this curve. So, if you want to have this, if you want to have a solution for this problem with the Neumann data on it, so the Neumann has to be the Neumann all along the boundary, if you are given a Neumann data, that is the flux should be 0, effective flux should be 0, that is what it says. Now, we will consider this rectangular plate problem, okay. What we consider is physically feasible one, once both sides, two sides we insulate it and one side also, 3 sides we insulate, other side we allow it to be we allow it to have something, okay, we allow it to have some flux, but that flux has to be, but that flux in such a way that the integral has to be 0, okay. So, we will see, we will pose that problem. So, the Laplace let boundary value problem definition goes like this: uxx plus uyy equal to 0, xy belongs to the rectangular domain D. You have this. Okay. Now, what you have, so I make uy is 0 here, uy is 0 here, and I have a ux equal to some function of y, ux at here let us say g2y, and here u2 ux is 0 here. So, let us make like this problem. Okay. Now, like this you by changing, so you make these 3 0 and here you keep 1. Okay. You can also, like earlier, you can break this problem into 4 problems. Okay. Only thing is f1 and f2 g1 and gy over this rectangle should be, that is underlying assumption. This is the necessary condition. Okay. So, if u is the solution, then necessarily you should have this boundary dou u by dou n dB has to be 0. So, this is a necessary condition. That means whatever the data f1, f2, g1, g2, that integral has to be 0. Okay. So, with those f and g's for which this integral is 0, if you are given, then if you are, they are all non-zero, then you break them into 4 problems like this. By 3 of them you take it as 0, you call this u1. Okay, here this if I call u1 problem, and u2 will be like earlier. So, remaining you take this 0 and other, so keep 1 is non-zero. Okay, like that you make u1, u2, u3, u4 problems and then combine it. Once you solve one of them and remaining 3 are similar, so and then you combine them to get the solution for this. So, we do one, so that is why we choose only one. So, one such thing where u1 ux is this boundary, you have this g2, but it is not but you cannot actually break it. Okay. So, you can only break see if you want to solve this problem. So, this has to be 0 to b, y is between 0 to b, g2 of y dy has to be 0 from the necessary condition, because other places anyway 0. So, this has to be true. So, if you are given f1, f2, g1, gy such that each of them integral is 0 for each f1, g1, f2, g2, let us say each of that integral, say 0 to a f1 of x dx is 0, 0 to b g2 of y dy is 0, 0 to a f2 of x is x dx is 0, g1 of y 0 to b dy is 0. So, if each of these are true, then I can break this into 4 problems. Okay, because necessary condition is anyway satisfied, even after breaking the necessary condition is still satisfied. Okay. Let us anyway choose this problem. If you have, otherwise also you need 2 ends, you need insulation, that is what is required. Okay. So, we can see that one. So, otherwise you will not be able to solve, you will not be able to break it into few problems, even though it is a linear problem you cannot do. So, after breaking each problem should satisfy the necessary condition. Okay. So, such a way you have to break it, but once you break it you should have two opposite ends should have 0 boundary conditions. So, 0 boundary conditions if you have, then only you can extract the Sturm-Liouville problem, you can solve by separation of variables, that is the idea. Okay. So, we will just take boundary conditions like this. This is the Laplace equation. Boundary conditions are ux at 0 y is 0, ux at a y equal to g to y, uy at x 0 is 0, uy at x b is also 0. So, I have 2 opposite 0 boundary conditions. So, this problem we will solve. Okay. So, g2 in such that integral 0 to b g2 of x dx, or actually y. Okay. It is anyway dummy variable, you can choose anything you want. So, dy equal to 0 such that g2 is such that and g2. So, this has to be true, then only you have the steady state you can find. So, you will have a solution that is physically feasible only if this is true. So, the solution we can now work out by separation of variables, that is a standard technique. So, you have let the solution be x of x, y of y, which is non-zero. You substitute into the equation, you break it so that you have x by x of x like earlier, okay, and divide it. Okay. You substitute this and you divide with this u. So, both sides you will get this one. This is equal to, so you put minus, bring it here. So, you have y double dash of y by y of y. So, it is both functions of x here, functions of y here, that cannot be same unless they are constant. So, this is a constant. So, now you have this Laplace equation becomes two ordinary differential equation like in the earlier video. So, you have this plus lambda x of x equal to 0, x is between 0 to a, and you do not have boundary data, boundary things are that is the first two boundary conditions. Okay. So, now for the other equation you have y double dash of y minus lambda y of y equal to 0. Now, the boundary condition 3, 4, boundary conditions 3, boundary condition 4 will give uy at x 0 equal to 0 will give me, what do you get, uy is xx into y dash of y, y dash of y at 0 equal to 0. So, this implies y dash of 0 is 0. Similarly, uy at x a, x b, right, uy at x b equal to 0 will give me y dash of b equal to 0. So, you have the derivatives are 0 for this Sturm-Liouville problem. This is the Sturm-Liouville problem as usual again, and you have, this is already in the self-adjoint form, simpler form. So, you can define the dot product as phi psi, because w is 1, because 0 to b, same 0 to b, domain is 0 to b, y is between 0 to b, phi x psi x bar dx. So, this is the definition for the dot product. Okay. So, once you have this, find the, so it is already in self-adjoint form. So, you can write, you can see that lambda is real. So, lambda is mu square, or lambda equal to 0, or lambda is minus mu square. So, lambda is mu square cannot be an eigen value. So, we can see this lambda equal to mu square, we will see this one. So, let us quickly we will just find out. So, lambda equal to mu square means y. So, the solution of this ordinary differential equation is, general solution is C1 e power mu y plus C2 e power minus mu y. So, if you apply y dash of 0 is 0 will give me C1 equal to C2. So, implies y of x is C1 equal to C2 means, so you get 2C1 cos hyperbolic mu y. Now, you apply y dash at b equal to 0 for this. If you do this 2C1 sin hyperbolic mu b, you have a mu comes out because of the derivative, this is equal to 0. So, sin hyperbolic mu b cannot be 0 because mu is positive, b is positive, 2 mu cannot be positive. So, it implies C1 is 0. So, that makes it, this is also 0. So, this implies lambda equal to mu square is not an eigenvalue, but lambda equal to 0 is an eigenvalue. So, this you can see by finding the general solution by putting lambda equal to 0, this becomes two derivatives of y is 0, the general solution is C1y plus C2. So, y dash of 0 equal to 0 will give me C1 is 0, so this is gone, and y dash of b is equal to 0 satisfied by 0 implies C2 is nothing. So, it is actually satisfied. Okay. When you do this, C2 is still arbitrary. Implies you have a non-zero solution. So, implies lambda equal to 0 is an eigenvalue. Eigenfunction is, corresponding eigenfunction is 1, okay, call this 1. So, this simply take C2 as 1 constant, that is 1. So, you also look at lambda equal to minus mu square, this part will give me general solution is, so general solution should be function of y, okay, y of y. So, you cannot write this x, y of y is C1 cos mu y plus C2 sin mu y. So, y dash at 0 equal to 0 will give me C2 is 0, okay, you can see that. And then, so that means this is gone. So, y dash at b equal to 0 will give me C1 sin mu b, mu comes out, okay, because minus has to be 0, that is the derivative, and put y equal to b. So, mu cannot be 0, if you want non-zero solution this has to be 0, this is possible for certain mu positive values. So, mu equal to n pi by b, mu is positive, n is from 1 to 3 onwards, okay. If we put n equal to 0, mu is 0, so that is lambda is 0. So, the lambda is 0 is an eigenvalue, so you can combine them. So, anyway you can write lambda n's are minus n square pi square by b square are eigenvalues. Eigenvalues are this, n is from I can also include 0, so from here, so 1, 2, 3 onwards from here, okay. So, that is lambda n square, and eigenfunctions are y n of y, which is equal to, so what are the solutions? What is left with this with arbitrary C1 you can take it as 1. So, you get cos mu is now n pi y by b, n pi by b into y. So, these are for n is from 0, 1, 2, 3 onwards. So, I have got eigenvalues and eigenfunctions. Now, you can look at a problem for xn's, okay. So, x, just look at the x problem, x, so you do not have to do the same way. So, what is the, now we look at the x problem, because you have one zero boundary condition you can remove one arbitrary constant here itself. So, how do we do this? X double dash of x plus lambda x of x, you consider only x double dash of x plus lambda x of x. Earlier we replaced with this lambda with lambda n's and then do it. So, you need not do this because you have a third boundary condition is zero boundary condition, okay. You can see that third boundary is rather first boundary, we use the boundary 3, 4, first boundary condition is 0. So, that makes it one constant we can nullify. So, the general solution of this x of x is C1 e power I root lambda plus C2, this is tricky. So, let us use the same way what we follow, okay. So, let us not do this one. So, given this lambda n, so for each n you have lambda, so x double dash plus lambda, lambda is minus n square pi square by b square x. So, x is depending, so now I am replacing lambda by lambda n, so this I label them as xn, xn double dash equal to 0 for each n is from 1 to 3 onwards, 0, 1 to 3 onwards, okay. This case what is your xn of x is simply a n e power n pi by b, n pi x by b plus b n e power minus n pi x by b. So, that is the general solution of this equation. Now, what is your u n of x y, which is x n of x into y n of y. This is simply a n e power n pi by b x plus b n e power minus n pi by b x, that is my x n of x. Y n is cos n pi y by b. See, cos here y n I can also, here I can include some other constant, but that constant C n, if I write C n into cos n pi y by b, if I take C n a n will be one arbitrary constant, C n b n will be another arbitrary constant. Anyway, two arbitrary constant will be, you can come. So, product of two arbitrary constant is still one arbitrary constant only. So, that way you can consider only 1 here. So, this is the solution for each n. So, now you can superpose the solutions, all these solutions as your solution u of x t, n is running from 0 to infinity. Okay. So, if you do this, let B the solution, B the solution. If this is the solution that satisfies, is already satisfying Laplace equation and the boundary conditions 3 and 4. Okay. Now, we apply 1 and 2 to find these a n's and b n's. So, apply first u x at let us see what is that u x 0 y is 0, u x 0 y is equal to 0 will give me, this is the boundary condition 1, u x 0 y is 0 will give me. So, now you can both sides you can differentiate u x x with respect to x, you get n pi by b comes out, you have a n e power and you are putting n equal to this, n equal to, so you are putting x equal to 0 after differentiation. So, it will be 1. So, you have only a n and this will be minus b n, okay, cos n pi y by b equal to 0. Now, both sides you apply these eigenfunctions, take a dot product with these eigenfunctions to see that n pi by b times a n minus b n will be 0 because right hand side is 0. You just multiply with the same cos n pi y by b and integrate from 0 to b, so that the constant has to be 0, okay, because that integral value is, it is something, it is b by 2. So, you have this has to be 0. So, this is true for every n 1, 2, 3 onwards, 0, 1, 3 onwards, okay, 0, 1, 2, 3 onwards. So, what happens if n equal to 0? N equal to 0, what you have is a n minus b n can be arbitrary, a n minus b n. So, a 0 minus b 0 need not be 0, okay, right, for n equal to 0. When you put n equal to 0, so this a 0 b 0, a 0 minus b 0, so you cannot do this. So, what is your solution? So, this implies a n equal to b n for n is from 1, 2, 3 onwards, because when you put n equal to 0, this can be 0, this is actually 0, right. So, you cannot say that this whole thing is 0, this whole thing is 0 is because n is here, when you put n equal to 0 is becoming 0. So, a 0 minus b 0 you cannot have anything, okay. So, only a n equal to b n you find. So, implies what you get is u of x t is simply n equal to 0 you can write it separately. So, a n plus, so a naught plus b naught, a naught plus b naught. So, you call this some constant when you put n equal to 0 plus this is some n is from 1 to infinity. Now, a n equal to b n. So, what you get is 2 times a n, because I am replacing b n as a n. So, you get cos hyperbolic n pi by b x into cos n pi y by b, okay. This is what you have. So, this is what you have. So, what is this now you have, this is your arbitrary constant. So, now you have an equation, now your solution becomes with boundary condition 1 and 3 4 and the Laplace equation. The solution is, so this is the solution that satisfies the Laplace equation and the boundary condition 1 and 3 4. So, I am writing here. So, this you call it some constant c naught plus this is a naught b naught is still arbitrary. So, a naught b naught, so that you call this c naught. So, and as a sum together it is an arbitrary, one arbitrary constant. So, you have c naught plus 2 times this n is from 1 to infinity, a n is an arbitrary constant, cos hyperbolic n pi x by b into cos n pi y by b, okay. Now, you apply the boundary condition 2, that is u x at a y equal to f or g. U x at a y is G2 of y. So, G2 of y, this is G2 of y. So, this will give me C0 plus 2 times sigma n is from 1 to infinity a n cos hyperbolic n pi. So, you are differentiating, right. So, you are differentiating this cosine function, it will become, so n pi b comes out and you have it becomes a sine hyperbolic n pi when you are putting x equal to a. So, n pi a by b. So, n pi a divided by b into cos n pi y by b. So, 2 you bring in, so that the whole this is the whole constant, this is the constant you will get, this equal to G2 of y. Now, this constant and this constants can be gotten from this eigenfunctions. So, what are the eigenfunctions? N pi y by b, n is now running from 0, 1, 2, 3 onwards. Okay. You simply multiply 1 and integrate from 0 to b. Okay. What you get is this sum will not contribute anything, only C naught. So, C naught multiply. So, C naught into b is actually equal to integral 0 to b G2 of y dy. I simply multiplied y 1, n equal to 0, cos n pi y by b is 1. So, I multiplied that both sides 1 and integrate from 0 to b. So, this will be 0 and this will be simply, that is what you have. So, implies C0 is 1 by b, b is non-zero. So, 0 to b G2 of y dy. But for in order to have the steady state, we know that this condition is already satisfied. So, implies this is 0, because this integral is the necessary condition to get the steady state. Okay. This is the necessary condition to have a solution for the steady state in the for the plate if you want. That means that is same as saying to have a solution, that is a unique solution. If this is non-zero, what happens? C0 is, so you cannot have physically, you cannot have this is a necessary condition, we have seen mathematically also. Okay. I have shown that this has to be 0, the contribution Neumann condition on the boundary has to be 0. So, this is 0. So, this implies, and what happens to the other boundary conditions, other if you apply cos n pi, n is from 1 to 3 onwards, you get 2 n pi by b sine hyperbolic n pi a by b equal to integral 0 to b G2 of y cos n pi y by b dy divided by cos square. So, that is also will give me integral 0 to b cos square n pi b by y, n pi y by b dy. So, this is because this value is b by 2. So, you have 2 by b integral 0 to b G2 of y cos n pi y by b dy. So, this gives me a n as, you can remove this thing. So, you can cancel b b, and what you get is 1 over n pi sine hyperbolic n pi a by b times integral 0 to b G2 of y cos n pi y by b dy. So, this is what you have for n is running from 1, 2, 3 onwards. Now, C0 is 0, C0 is 0. So, this implies C0 is 0. So, this together this if you put it into this is the required solution. So, this is the required solution that satisfy all the boundary condition with C0 is 0. So, you have 0 and you have this a n with a n being this one. Okay. This is how you can solve Neumann data on the boundary for the Laplace equation. Okay. So, as a mathematical problem for the Laplace equation, if you are given a Neumann data, so what you need to see is that necessary condition you have to verify first of all the boundary data, Neumann data should be that integral has to be 0, then you will have a solution. Otherwise, you may not be able to work out the solution. Okay. So, as a physical problem, or that we have seen as a physical the heated plate, when it reaches the steady state, and whatever so see physically what it means is another thing is you have a plate 0 here 0, so all the 3 places 3 boundaries you insulated, only here is not insulated, flux is you allowed the flux, that means some part of the boundary flux, so heat is coming in, some part of the boundary heat is going out. So that is the meaning of that integral 0 to b g to y dy is 0. So the flux is net flux is 0, that means whatever comes through that same boundary, whatever heat comes in, a net amount of heat comes should be same as net amount of heat that goes out of the same boundary. Okay. So this is how you can, so you can see that then only it will reach the steady state, then the steady state temperature of the plate is the solution of this problem. So as a separation of variable method we can apply and get it like this. Okay. So this is how we can solve the Laplace equation in 2 variables, and we will see in this, so what we have seen is for rectangular Cartesian coordinates. So in this simpler domain like rectangular domains you can use this Cartesian coordinates and work out separation of variables. We can also work out certain other domains such as circular domains, circle, interior circle, exterior circular domain. We will see in the next video how to find the solutions for the Laplace equation in the curved domains such as circular domains. Circular, basically circular we will use the polar coordinates. Okay. Thank you very much.